Hola everybody, welcome to video number 7, there's only one more I promise, of the basic electrical series. Today in this video we're going to talk about parallel circuits. We're going to talk about the math behind them, and we are going to talk about the rules and characteristics behind these circuits. So what is important to know is there's some characteristics that remain the same. So that teeter-totter between amperage and ohms, that's always there. Always need to have continuity and grounds and things like that. But some things that do change is from series where we only had one path for current to flow. In a parallel circuit, or if I have multiple loads wired in parallel, current has more than one path to ground. The way I like to think about this is as if you're thinking of roads that people drive on. So depending on what kind of neighborhood you live in, if you live in maybe a suburban neighborhood that is very large, lots of tract homes, there might be multiple ways to get to your house. Depending on where you live in the neighborhood, right? You might have 4 different ways to get back to your house. So if they were to block one of those roads, you can always go around. As to where that would be more like parallel circuit versus a series circuit is, say you live somewhere in a canyon and there's only one way in and one way out. And so if a road is blocked, you're not leaving. You're either not getting home or you're not leaving home. So that's more like a series circuit, right? So parallel circuits, current has more than one path to get to ground. And this is a really fundamental thing to remember, because in a series circuit, if I unscrew one light bulb, they all went out, right? In a parallel circuit, and I'll show you this on the circuit board at the end of this video, the parallel circuits are going to have multiple paths. So if I lose one of these light bulbs or I lose one of these paths to ground, electricity still has this path. And so this light bulb would not be affected by that light bulb. And that's important to know, which is why we utilize parallel circuits so much in automotive. Imagine if you're driving somewhere in the middle of the desert, it's super dark, and one of your headlights goes out. If they were wired in series, you would lose both your headlights, even though it was just one bulb that went out. That's why we wire them in parallel, so your headlights can, one can remain if the other does go out. So if you do lose a headlight, you still have the other one, because they are 2 separate branches and they have their own paths to ground, which is really nice. So that's why we use parallel circuits a whole lot. Now let's start to get into some of the math. There's a couple of these rules that can get a little tricky, so let me help you navigate through them. First off, we have some stuff about Tca and Tcr. And I should have put some of these in a particular order, and now I'm looking at them. I did them in the order that I wrote them down in, but let me switch them around so it's a little bit easier to talk about. I'm going to talk about both the Tca rules at the same time, and then we'll get to Tcr. But I want to talk about source voltage. So back when we were using series circuits, we know that the voltage had to be split, right? So depending on the resistance values, the one with more resistance generally used up more voltage. Now in a parallel circuit, and this is why, again, an advantage of parallel circuits, in a series circuits, the more loads I add, Tcr is the sum of resistors, and Tca is based off of Tcr. So back to that teeter-totter. In a parallel circuit, resistance is not the same, and we have more than one path. So cool part about parallel circuits is that source voltage is the same for each branch. So we've got source voltage coming out. We know a fuse and a switch is not using up any voltage. So it goes down here. It doesn't split up. It doesn't say, all right, 6 volts here, 6 volts there, right? No, we have 12 volts going into this bulb and 12 volts going into that bulb. So in a parallel circuit, each branch gets source voltage. So we can add 1,000,000 bulbs and the brightness of those bulbs is not going to dim, as to where if you watched in the previous video, the series circuit, as we kept adding bulbs, the bulbs got dimmer and dimmer, and that has to do with that TCR. The higher TCR is, the lower amperage. Not to mention, we're taking voltage and we're having to split it. So there's a couple of factors involved. With parallel circuits, we're not splitting voltage. Instead, we're sort of splitting amperage, and I'll explain that here in a moment. But it's important to note that each one of these bulbs is going to receive 12 volts or source voltage, and it's going to use up source voltage. So up here, I've got VD1 and VD2. We'll talk about it, and we'll show the math, but there's no need to figure that out, because in a parallel circuit, each one uses up source voltage, source voltage, source voltage. Whether there's 2 branches or whether there's a million branches, each one is going to use up source voltage. Now, things are affected, and we'll show that in the board. Amperage in this case is going to get affected, and we'll talk about that here. Now, here is what is important to know. TCA, total circuit amperage, is going to split up. Remember, whatever comes out is going to come back in. But in between, in a parallel circuit, TCA is going to split up. This is all going to be dependent on resistance. And hopefully the video glare is not too bad. But TCA splits between branches based upon resistance. Now, in this case, we've got resistance values that are exactly the same. So you would imagine amperage is going to split in half. And that's exactly what's going to happen, essentially, from your TCA. So I'm going to come back and show you that mathematically. But before we do that, let's look at TCR. Again, I started going out of order here, but this is the last one I haven't spoken about yet. And it's crazy because it's exactly the opposite almost of a series circuit. So with series circuits, TCR is the sum of all resistors. Well, in a parallel circuit, TCR is not the sum of all resistors. So I am not adding them up. Instead, TCR is always lower than the lowest resistor. So if these are 2 ohms each, it needs to be, or it must be, less than 2 ohms for the entire circuit. Electricity is lazy, and it will always choose the path of least resistance. And so the lowest resistance part of the circuit is going to determine the amperage for the entire circuit in a small chunk there. I don't want to get too into it. Again, that's more for an electrical class, but TCR is always lower than the lowest resistor. Now, how are you going to find that out? Because you can't just add them up. I will show you, I'm going to show you 2 different ways, 2.5 different ways of how to figure out TCR and TCA. And let's go ahead and do that. So now that we know the rules, we're going to come back and I'm going to keep pointing at them, but let's practice them. So the whole point is to find TCA and TCR, right? How do we do that? So I'm going to show you the very first sort of method to this, and it is an equation to use. The equation looks like R1 times R2 over R1 plus R2. And that's going to give us our TCR. If that makes sense. Now, what is R? R is actually referring to resistance 1 and resistance 2, whatever they may be. In this case, they're light bulbs, but they could be motors, they could be horns, doesn't matter. As long as it's a parallel circuit and we're trying to figure out TCR, this is the equation you're going to use. R1 times R2 and R1 plus R2. So remember that. I don't have enough room on my whiteboard, so I'm going to apply that here. R1, 2 ohms, times R2, which is 2 ohms. Got 2 times 2, over R1 plus R2, so 2 plus 2. Pretty basic, right? So 2 times 2 is 4, and 2 plus 2 happens to be 4. 4 divided by 4, we know, gives us a TCR of 1 ohm. That's weird, but they're 2 ohms each. Remember, TCR is always lower than the lowest resistor. And I want you to remember something about parallel circuits. Think of parallel circuits like a freeway. When they are doing construction on a freeway and they add lanes, not during the construction. And if you live in California, this doesn't really apply because we always have traffic, except for now because of the Rona. But as we add lanes to a freeway, traffic tends to dissipate, right? We have less resistance. If we take lanes down, say during construction, if I took a 4-lane freeway and I took it down to a 1-lane, what happens to resistance? It gets jam-packed. Everything's all backed up, right? And so what we're doing in a parallel circuit with branches is we continue to, if I add a branch, I add a lane to that freeway. So the more branches I add to that freeway, you'd think I'm adding resistance. How is resistance going down if I'm adding more bulbs to this parallel circuit? Because you are adding lanes to a freeway. And you're adding more branches for current to flow. Therefore, you are decreasing the resistance in the circuit. Hopefully that makes sense. And so, and you find this out when you're at home and you try to plug too many things into one outlet, right? Say you put a power strip into an outlet and you plug a blender, a toaster oven, and your NutriBullet or whatever, and you turn all of them on at once. They're going to pop a circuit breaker, aren't you? Well, why would you pop a circuit breaker? Well, if you watch the previous videos, you'd know that the amperage spiked. That's why you had to reset your circuit breaker. How the hell did amperage spike? You kept adding lanes to the freeway. Therefore, electrical resistance goes down and amperage spikes up. So, I know that's a lot to remember, but hopefully that makes sense. So, what our total circuit resistance is 1 ohm, even though we have 2 branches of 2 ohms. But we know it's correct because it is lower than the lowest resistor. So that's how we explain that. Now, the problem with this way is if I have more than more than 2 branches, my equation must change. And what starts to happen is my equation looks something like 1 over R1 plus 1 over R2 plus 1 over R3, and then however many branches. So if I've got 5 branches, then I've got plus 1 over R4 and then plus 1 over R5. We call this the reciprocal formula. I am not going to go down that path again. This is a basic electrical, so I really want to make this easy. So I'm going to show you the easy way. And if you are interested in the mathematical equation, go ahead and take our electrical class and we'll show you all of that fun stuff. But this is our reciprocal formula. If you'd like to use that, you're more than welcome to, but fractions make a lot of people really uncomfortable. So let me show you a nice and easy way. The easiest way to find this is going to be to use what a lot of books will call the hand method. Now, that leaves a lot open to interpretation, but what essentially it's referring to is instead of figuring out TCR first, you figure out TCA first. And this makes things a lot less complicated. So let's go through, and instead of finding TCR, we'll get rid of our R figures. We want to know TCA. This is easy to do as long as you know your source voltage and your resistance, because all you have to do is cover up all the other branches except for one at a time. And now we're going to treat this just like a simple circuit. And we've already done that math, right? If I've got 12 volts in my Pokeball Ohm's Law pie chart here, I've got 12 volts and I've got 2 ohms. Again, this branch doesn't exist. That gives me 6 amps in this branch. 6 amps in branch 1. Now, for the second branch, I'm going to figure out the same thing. The math is the same because the numbers are the same because the resistance is the same. So we know that 2 ohms and 12 volts gives us 6 amps in that branch as well. And this last rule down here told us Tca is the sum of branch amps. So instead of finding Tcr, the number is going to be the same, by the way, for Tcr. Tca, we're going to get rid of our Pokeball here so we don't get confused, is the sum of branch amps. So we take 6 amps in branch 1 and add it to 6 amps in branch 2, and that gives us a total Tca, or total circuit amperage, of 12 amps. And then we can work backwards. So if we know any two, we can figure out our third. So we found amperage first. You work backwards. Again, what we're looking for here, I know we already calculated it, but I'm showing you a different way. So we're looking for resistance. So we'll put that in there. We know we've got 12 volts, and we know that we have a total circuit amperage of 12 amps. 12 divided by 12 is going to give us a TCR of 1 ohm, which we found out the other way as well, but in my opinion, this is the easier way. So the hand method, instead of using the formulas, are finding amperage for each branch individually and then adding them up to find TCA and working backwards with Ohm's law, so we don't have to deal with really any fractions at all to deal with this. Now, again, I'm using really basic numbers just to sort of get the point across. The numbers are not going to look the same as if you were to get the ohm reading from your headlights. It's going to be decimal. And so this math is going to be a little bit more messy, and you'll need a calculator. But just to show, that's how you would find TCR, is by finding TCA first for the hand method. Now, with that, I'd like to just do a couple more. I'm going to do one more 2 branch, and then I'm going to do 1 3 branch so I can show you how to do that on that one. The same principles are going to apply though. So let's go with, we'll get rid of these numbers here and these numbers here. Let's say the numbers are different, right? Because the amperage ended up being the same, and so it was a little too easy. Let's go with, let's say this one was 3 ohms, while this one was 6 ohms. How about that? Again, I'm gonna, if you'd like to pause the video and use the formulas, you're more than welcome to, or pause the video and do the hand method. But again, I'll give you guys a chance to do that, figure out TCA and TCR. And if you remember, VD1 and VD2 of bulb 1 and bulb 2. So pause that right now, and then we'll do it together. All right, hopefully you did it and you didn't just watch this through, because that's being lazy. And what are you here for? Why are you watching this boring stuff if not to try to really get it? So hopefully you try to figure this out on your own. If we have one branch with a 3 ohm bulb and a second branch with a 6 ohm bulb, using the hand method, we would have a simple circuit here, and we are looking for the amperage in this circuit. We know we've got 12 volts as our source voltage going into this branch. We know for this one branch I've got 3 ohms. We take 12 and divide that by 3. That's going to tell us that we have 4 amps running through this branch. Now, again, same thing, but down here, our bottom branch instead has a 6 ohm bulb, but we still have 12 volts coming straight in. So we take 12 divided by 6. That is going to give us 2 amps in that branch. And back again, TCA is the sum of branch amps. So all we have to do is add 4 amps from that branch and 2 amps from that branch. And that will give us a total current of 6 amps in our circuit. Now that we know our amperage as well as our source voltage, we can go back and find our TCR. we are looking for resistance. So we know we've got 12 volts. We have a total current, or I'm sorry, total circuit amperage of 6 amps. That tells us our total circuit resistance, again, because this is 12 divided by 6, is going to be 2 ohms. And we know that's right because it's lower than our lowest resistor. So our lowest resistor was 3 ohms. 2 ohms is lower. And so we know we did it correctly. All right. So I'm going to draw one more up here as a 3-branch just to challenge you a little bit. So we will go ahead and add an extra branch here. Let's just start new. All right. We've got, oops. All right. Let's say on this 3-branch circuit, we have 4 ohms, 2 ohms, and 4 ohms. All right. The same exact things apply. So once more, pause your video right here. Figure out Tca, Tcr, and I completely forgot to talk about VD1 and VD2 on the last one. So let's make this one VD1 and this one VD2. How much voltage is being used up on VD1? How much voltage is being used up on VD2? So pause the video right now, figure that out on some scratch paper, and then we'll do it together. All right, hopefully you did that. Let's work this out together. All right. So let me use the correct color here. Again, using the hand method, if you wanted to use the reciprocal formula, go on and live your best life. But for everybody else, so I don't confuse anybody, we're just going to continue to use the hand method for now. So we'll pretend that the rest of the circuit doesn't exist, and we're going to find the amperage for branch number 1. And so if we draw our Ohm's law pie chart, again, we're looking for amperage, so we'll put a question mark there. We know we have 4 ohms going through that bulb, and we know we've got a source voltage of 12 volts. So how much amps do we have going through that circuit? We have 3 amps, right? Because it's 12 divided by 4. So 4 goes into 12 3 times, 3 amps for that branch. What's really nice is since 4 was down here as well, we can do that one, and we get the same exact number. So we can be kind of lazy there. But in the middle, our number is different for resistance. So obviously the amperage is going to be different. So we'll go ahead and block these two. We'll go ahead and fill in our 2 ohms there. So our math becomes 12 divided by 2, and we have 6 amps running through that branch. Now we know all the branch amperages. Let's add them up to find Tca. So we've got 3 plus 6 plus 3 is going to give us a Tca of 12 amps. Notice the amperage went up, even though we added a 3rd branch. Lanes to a freeway, my friends. Lanes to a freeway. The more lanes, the less resistance, and more amperage we're going to get. So if you're going to guess, hopefully you figured out Tcr already. Let's go back and find it with Ohm's law pie chart. We know we're looking for resistance, so we'll put a nice little question mark there. We know, because we added up all our amperages, that we have a Tca of 12 amps, and we know our battery has a source voltage of 12 volts. 12 divided by 12 gives us a total circuit resistance of 1 ohm. So resistance went down and amperage went up after adding another bulb. Fancy that. That's why parallel circuits are great, but it's important to know the characteristics behind them so you can anticipate their behavior when you start to do stuff. If you're going to add a circuit onto something, let's say you're adding an aftermarket set of fog lights, or you're adding an aftermarket horn or something like that, if you are adding too many lanes to that freeway, you could end up increasing amperage on a circuit if you don't do it correctly, enough to pop a fuse. And then you'll wonder why you're popping fuses. There's no short circuits because you added too many branches to the freeway. Remember, adding too many pieces of equipment to the power strip. It's the same thing. So you're going to need to wire something differently if that's the case. So that's why I think it's important to know some of these fundamentals. So that is parallel circuits in a nutshell. Theoretically, I'm going to show you on the board here when I flip the camera what these characteristics look like in real life. So we'll go ahead and flip that camera. Okay, so what we're looking at in this portion is our parallel circuit in real life. So you guys have seen my beautiful drawings, but what does a parallel circuit look in real life? So let's just do a quick review of what we're looking at here. Here is our fuse close to our power source. I chose to put my switch in front. We could have went ground side. Doesn't matter. Again, switch is just simply opening or closing a circuit. Now what's important here is I've got my power path going in straight to here, but we are distributing it. Each one gets their own power path and their own ground path. And so what we're looking at here is power coming in here to this bulb, but also branching off and going down to this bulb. And we also, out of each bulb, they have their own path to ground. So this one can go to ground or this one can go to ground. So we've got multiple paths for continuity, which is really cool. Now we noticed that in the series circuit video, we saw that both bulbs went dimmer when we added the bulb to the simple circuit to make it a series circuit. So let's check this one out. We've got two bulbs. These are actually pretty darn bright, I'd say just as bright as the simple circuit. If anything, it could potentially be a tad brighter, but we'll get into that. So we're looking at our parallel circuit here. Let's just go ahead and play around with some of this stuff. So right off the bat, we know that they're not dim. They are still bright. First thing, why? Well, we know that source voltage doesn't have to get split up. It didn't increase, just it doesn't have to get split up. This one gets 12 volts. This one gets 12 volts. It's Oprah of 12 volts. Everybody gets 12 volts. Check under your seat. So there's that. Not to mention, remember, in a parallel circuit, as we add branches, we are adding lanes to a freeway, essentially. And so we are creating less resistance in the circuit. So we're looking at an increase, a decrease in total circuit resistance, therefore an increase in amperage. And voltage is distributed equally, and it is full source voltage to each branch. And so these are a couple of reasons why we're looking at some bright bulbs right now. Now, remember in series circuit, if I disconnected one of my bulbs, they all went out. Well, let's check it out in this one. Look at that. Our other bulb still works. Let's try the other one. The other one still works. And the reason for this, remember, each branch has its own path for continuity. It has its own power path and it has its own ground path. It's a strong, independent branch that doesn't need no other branches to help it out. So it doesn't matter what happens, which is why we wire most of our lights in the car in parallel rather than series. That way you don't lose all of your headlights when one goes out or all of your brake lights when one go out. So those are a couple of cool things to note about parallel circuits. Now, in the last series circuit video, we had our villain that sucked all the voltage, our 1152 bulb, right? Well, let's check it out and see what it looks like when we add this guy in place. So we'll go ahead and turn off our circuit. We will go ahead and disconnect our ground. We'll go ahead and add an extra path. So this one can have its own ground. And then we need to provide it its own power source, or I'm sorry, power path, not power source. So we'll go ahead and add a little branch here. Hopefully that comes out okay there. Now let's see what happens. In the series circuit, this one stole all the voltage and these were barely hanging on. Let's see what happens here. What? So crazy thing, and it's actually really hard to see on camera, is at first they all look very much the same voltage, but these two are actually a hair brighter. What? Than this one. Now we know that in a series circuit, our 1152 was brighter because of what? It used more voltage. Why did it use more voltage? It was a hungry little light bulb. No, it had more electrical resistance, didn't it, than these ones. So the arbitrary numbers we had for our bulbs were 1 ohm, 1 ohm, and 2 ohms, right? Let's sort of stick with that and let's show why these two are now just a hair, and I know in the video they look probably pretty darn the same. These two are just a hair brighter than this one in a parallel setting. So if this one, whoops, sorry here, let me go ahead and move my switch so we can have a little bit more space to look. If I've got in my first bulb, we're looking for, let's say we want to find amperage in each branch. We can do that. So we'll go ahead and draw our little handy dandy Ohm's law pie chart. If we're looking for amperage, we know that it's going to be that bottom left corner in each one of these. What do we know? We know they all are getting source voltage. They all drop and use up source voltage, right? Now we said that this one was going to be 1 ohm, and this was the 2 ohm bulb in the series circuit. So let's maintain the same numbers just for continuity. We've got 1 ohm here. That gives us 12 amps. 12 amps. Going through this one, we know this one's the same, so we'll just put the same number. 12 amps going through each one of these branches. That is a lot of amperage compared to what we were looking at before. And if we look at our 2 ohm bulb, now we are looking at 6 amps. So now this one, even though it's just a hair dimmer, that is not because of voltage drop. They each get 12 volts. So we know that voltage has nothing to do with it in this case. It has to do with the amperage in this branch, because the amperage in each branch is determined upon the resistance, as it always is. So that's some cool stuff about parallel circuits. So that is all we're going to do on the board here. I will show you guys what the voltage drop looks like and all that good stuff with the DMM next week.